Loud. Okay, so thus far we've spoken about mass and mole, number of atoms conversions. That was chapter 3. So we learned how to use mass to essentially count atoms and figure out how much is there. In chapter 4, we looked at chemical reactions, right? We looked at 3 different types of reactions in the classification. And then in chapter 5, we did all the thermochemistry, right? So we have now gone through 3 chapters. So we're up to now sort of the last chapter before we get into quantum mechanics, which is modern chemistry. So this is sort of the last classical chapter that we'll cover involving matter. Okay, so before we start, any questions? Okay, all right, so let's go ahead and start. So we're going to start with gases. We've talked already when we were dealing with mechanical work. If you recall, in chapter 5, we said that mechanical work or gas cylinder work or compressive work is minus P external times delta V times the change of volume. So this was for the situation where we have a cylinder, or at least it works for a cylinder. Works for other situations as well. So we have a cylinder with a piston. And that piston can be pulled in or out. And then we have some mixture of gases, or maybe even just one type of gas inside there, okay? And so delta V, we said, was the final volume minus the initial volume. And then the external pressure was this applied force onto the piston. So it's what's pushing down on the piston. And we said that the external pressure was equal to the applied force. So I'll put applied. Divided by the surface area of the cylinder. CYL for cylinder. Let me turn this off. Oh, that is off. Okay. All right. So force over area. Typically, people just write that as force over area. Okay. And what we said was that if the piston is not moving, if the piston is stationary, then what that means is the pressure upward applied by the gas is equal to the pressure downward by the external force. Right? That's essentially what the idea of mechanical equilibrium is that if you are pushing up on an object, right, it'll move. On the other hand, if there's a force pushing down, it'll move downward. But if those two forces are in balance, we would call that equilibrium. And those balanced forces, the net force is essentially 0. So the piston will remain stationary. And that's essentially what's happening. It allows us to actually measure the pressure of the gas without actually knowing what it is, without measuring it. We can figure it out if we can measure the external pressure. They're equal to each other. Okay. So we're going to talk a little bit more about pressure in terms of what we call pressure conversions, which are, quite frankly, they're pretty easy, especially if you've gone through chapter 5 already. If you're already doing, work calculations and heat calculations and all that, then pressure conversions are very simple. Essentially, what we would say is that there are many different units of pressure that are used, just as there are many different units of volume or length or time. So pressure has many units. So I'll write it out as pressure measurements have many units. Okay, so I'm going to just write a few of them down. 1 standard atmosphere. Now, a standard atmosphere is essentially the atmospheric pressure that we experience from the Earth's atmosphere at sea level. Okay, so we could be kind of detailed about it has to be done at a certain temperature and it has to be done under certain weather conditions, but it's essentially the pressure of the atmosphere. Now, New York City is essentially at sea level. It's very close to sea level. It's not a very, it's not a mountainous area. And so it's pretty close to sea level. So the pressure in New York City, and if there's no storm coming in or leaving, is generally pretty close to 1 standard atmosphere. So we're going to call that 1 ATM for short. Okay, but there are many other units that are used, and some of them are done for historical reasons, some of them are done for practical reasons, and some of them are done for convenience of calculations. So we're going to have kind of a mix of them. So one that you may have heard is called the pounds per square inch, which is abbreviated PSI. Okay. Pounds is a unit of force in imperial units per square inch. So it's pounds per square inch. A square inch is an area, right? Like a square foot is an area, a square yard is an area, a square mile is an area. A square inch is also an area. So it's really pounds force per divided by square inch area, force over area, right? And it's about 14.7. There's another one called a millimeter of mercury. And so a standard atmosphere is 760. This is a definition, so it's an exact number. It's not 2 significant digits or 3 significant digits. It's a definition, so it's an infinite number of significant digits. Millimeters of mercury, and that's abbreviated as mm for millimeters, and then Hg, well, that's the symbol of mercury, right? Now, this is sort of an odd unit, or it may appear to be odd because it's a length, right? A length, and it's a length of a material. So you will see this in meteorology. You'll see things like inches of water or inches of mercury. It has to do with how pressure historically has been measured. So I'll talk about that in a moment, but this is another unit, completely different units, right? Pounds per square inch, which is force over area, related to millimeters of mercury, which is the height of a liquid. So it's sort of odd, okay? The millimeter of mercury is also called, for historical reasons now, it's called a torr, 760 torr, which itself is an abbreviation for Torricelli, which is the name of a physicist that worked in Italy hundreds of years ago. So it's just typically abbreviated as TORR. Torr. Okay, so the number of millimeters of mercury is equal to the number of torrs. It's identical units, just a different name for it. Now there's also, I'm going to write this again, 1 ATM is also equal to 101.325 kPa, which is abbreviated for kilopascals. And this is one that you should definitely be aware of because it's very commonly used in some of the ALEKS problems, the KPA, kilopascals, okay? So 101.325 kilopascals. So notice that has, it has a prefix, K for kilo, which means 1,000, right? So this is really the same thing as 101.325 times 10 to the 3 kilo pascals, PA for Pascal. Again, Pascal is named after a scientist and mathematician. Okay, so you got pascals or kilopascals. Kilopascals you'll see more often than pascals, but they both exist. Now, I'm going to give you one more kind of definition here of unit conversion, which is if you look at that, 101.325 is pretty close to 100. And, it's only off by about 1%. So often people will define another unit called the bar, 1 bar. So you'll see this one too. Bar is equal to 100 kilopascals. So all they did was round it off. They said, hey, 101.325 is not very convenient. That's so close to 100, it's tantalizing. So what they did was they said, let's just, instead of using the atmosphere, let's have another unit called a bar, which is just 100 kPa, 100 kilopascal. Okay. So those of you that do physics or engineering, you may see that one as well, because, if we're measuring pressures that are very high, so let's say I'm measuring the atmospheric pressure of Jupiter halfway through its atmosphere, the pressure might be thousands of atmospheres. So, the difference between 2,324 atmospheres and 3,200 atmospheres is pretty small. So they'll just use bar. They'll just say it's, 3,200 bar, just to get numbers rounded off a little bit. Okay. So those are some of the units. There's other ones as well out there. There's gigapascals. So there's these experiments where people do, where they really want to measure what happens to matter, to material, if you put them under enormous pressure. So it's kind of cool. What you do is you take a diamond and then you take another diamond and you do a really good job. You have someone who's an expert at this, an expert jewelry person who just like really polishes off these diamonds so that they're flat at the edge. But this flatness is really small. I'm exaggerating how big this is. This might only be like, 100 micrometers across, which is, I guess, less than a hair width across, right, on the edges there. And then what they do is you put it into a device that you can screw them. So this one screws up and this one screws down, so you can get them really close to each other. And then you put something in between. It could be whatever you want to study, ice or plastic or dye molecules, whatever you want to study. And then you twist these diamonds together. And what happens is pressure is force over area, right? Pressure is force over area. So what happens is, even though these are just little diamonds and you're applying a force, the forces can be pretty large, but not extremely large, because eventually the diamonds will break. But what you can do is you can get, these areas so small because it's a little tiny diamond, 100 micrometers across. This is really small. So what happens if this is really, really small and you make the force large? This is huge, right? If you put a large number in the numerator and a small number in the denominator, the pressure is very large. So now you can apply enormous pressures to whatever material you want to study. Diamonds are transparent. They allow light to go through. So you can send laser beams through there, and lasers can, interact with those molecules that you're putting under enormous pressure. And, the thing about diamonds is that you can cool them to enormous, really low temperatures too. So you can study these molecules at low temperatures and they'll start behaving differently at low temperature. So you can do these cool experiments. And there, the pressures are huge. You might have what we call gigapascals, or even, kilobar. Kilobar. I don't know if you can go to megabar. Maybe you can go to megabar and gigabar. I'm not sure if you can get that high, but you might be able to. These enormous pressures. Okay. So there are many different units used. These ones are sort of the common ones, but you'll see other ones out there as well. I don't think your Alex has any PSI in it. I could be wrong, but I don't recall that there's any PSI. PSI is used in the United States for inflating tires and stuff like that, right? But having said that, there's other units. So let's take a look at a unit. A unit conversion. Okay. There we go. Interconverting atmospheres in kilopascals. There you go, right? Now I had a tendency, in doing problems in textbooks to round it to 101.3, but I think you want to use the 101.325 for ounce. So here we go. The vapor pressure, we haven't talked about what vapor pressure is. Well, actually we haven't talked about what vapor pressure is. Of solid iodine at 25 degrees Celsius is 0.1889 kilopascals, kPa, right? There's your kPa, kilopascals. Calculate the vapor pressure in atmospheres and round your answer to 4 significant digits. So, I'm going to talk just for a moment, just as a sidebar about vapor pressure, because it's kind of a cool thing. We'll talk more about it later in the chapter. But let me just quickly come up here and talk about vapor pressure. But here's what happens. If you take a container and you put a substance in it, let's say it's a solid iodine. Remember, iodine is a diatomic, right? So it's a solid. And iodine is a solid at room temperature, but it melts at a pretty low temperature. I forget which temperature it melts at, but it's not very high. It will melt. But here's what happens. Even solid iodine, if you were to close off this container and put a little detector in there, which measures pressure. So we'll put a pressure sensor inside. There's all kinds of cool pressure sensors out there. I think even the phones now have pressure sensors in them. If they don't, they will soon. So the sensor will measure the pressure, but it's up in, it's not at the bottom, it's in there, so it's going to be measuring the pressure of a gas, right? So here's what happens when you close that off. Some of the iodine will actually vaporize, turn into a gas. It's actually called sublimation. When something goes from a solid to a gas, it sublimes. And so you'll have little iodine molecules in the gas phase. So you'll have a gas, and this is gaseous iodine. And if you measure the pressure of that gas, that is called the vapor pressure of iodine. Now, just again, to put it into perspective, atmospheric pressure is 1 atm. We all kind of know what that is, and that's at sea level. I forget what the atmospheric pressure of Mars is at the surface, but it's really small. On Mars, it's something like 0.003 atm or something like that. It's like 3% or 2%. That's 0.3%, right? So yeah, I think it's like 0.3% of the atmospheric pressure at sea level for the Earth. It's really low. It's still an atmosphere there, but it's really small. Something like that. You can look it up. You can Google it. But that's what the vapor pressure is. So the vapor pressure is the gaseous pressure of a substance that's in the gas phase that came about from essentially the vaporization of a solid or a liquid. So we often refer to this vapor pressure in everyday language with water. We are, even though you may not have thought about it, water has a vapor pressure. And we often refer to that as relative humidity, right? The humidity is the amount essentially of vapor water vapor above a liquid or above even a solid. So even if you take a block of ice, some of the water will sublime into a gas, and you'll have the vapor pressure of water. So we'll look at that a little bit later. There's a type of calculation we have to do in the laboratory experiment, where we look at vapor pressure of water. Okay, so that's where that's coming from. Okay, So other than that, it's a pretty simple calculation. They give us the vapor pressure at room temperature, 25 degrees C is about room temperature. It's 0.1889. Now think about it. 1 atmosphere was 101.325 kPa. This is 0.1 kPa. That's pretty low. So we're not claiming that a lot of that iodine is boiling off into a gas. Only a tiny bit of it is, because that's a pretty low pressure. But it's a very simple conversion to do. All you need to do is to look up the conversion factor. So if our pressure is 0.1889 kPa, all right? If we want to convert it to atmospheres, well, 1 atmosphere, it's actually, I think, called a standard atmosphere or a normal atmosphere. There's a slight difference between standard and normal, but we don't need to worry about, is 101.325 kilopascals. So if we want to convert it to atmospheres, we're going to put the atmosphere on the top in the numerator, and then we'll put kPa in the denominator. So 0.1889 kPa times, oh, sorry, I almost put the wrong one there, right? But you would see that very quickly. If you put kPa, you'd see very quickly through the unit dimensional analysis that that was not the right way. We want atmospheres, so we're going to put this on top. And then this is 101.325 kPa. Okay, kPAs will cancel and we'll have atmosphere. It's going to be a pretty small number, right? 0.1889 divided by 101.325 is really small. It's 1.864. See, I just rounded it to 4 significant digits as they asked, because this one has 4. The conversions, you can assume they're an infinite number of significant digits. So you just need to worry about the measurement they gave you. This is times 10 to the negative 3. And then you can have atmosphere. Very low pressure, right? It's not very large. But I don't know. I don't know what breathing iodine, even at that low pressure, will do to you. It might be toxic for all I know. I'm not sure. Okay. So there you go. So there's a unit conversion. And let me see here. Let's take a look at a second one. This one involves converting atmospheres and torr. Okay, so kilopascals, atmospheres. Now we're going to do atmospheres and torr. So notice this one. They say it's torr. Okay. The partial pressure, we haven't talked about partial pressure either. I'm going to actually ignore that term partial pressure. Just consider it pressure for now. We'll talk about that later. The partial pressure of nitrogen in the atmosphere is 593 decimal millimeters of mercury, right? mmHg. And typically people don't put a space between the M, the second M, and the H for mercury. I'm not sure why. Because it's, I guess, 1 unit. So you wouldn't want to put a space if it's just 1 unit. So there's your pressure in millimeters of mercury. But remember, the millimeter of mercury is the same thing as a torr. So that's actually also telling you what the pressure is in torr. Calculate the partial pressure in atmosphere and torr and round it to 3 significant digits. Again, why 3? Well, you got 3 right here. And then the conversions are exact conversions, they're exact values. So you don't consider their significant digits in the analysis. Okay. So let's stop that one and come over here. What was it? 593, right? So 593. So our pressure is 593 millimeters of mercury. But remember, that's the same thing as a torr. They're the same. So that's 593 torr. That's an easy one, right? They're exactly the same. And then we just have to remember that number, 760. So 760 torr. You can also write 760 millimeters of mercury is equal to 1 atmosphere. So actually, that shouldn't have a decimal there, right? Because that would make you think it only has 3 significant digits, but it's an exact definition. So it's actually This is exact. Okay. So 593 torr, we want to go to atmospheres. 1 atmosphere is 760 torr. So it's going to be less than an atmosphere, right? 593 over 760 is going to be like 6 over, what is that? 600 over 800, I guess. 600 over 8 is 0.75. So a little bit more than 0.75, maybe 0.8 or something like that. 593 over 760. Yeah. And then 3 significant digits, it says. So 780, torr cancel, and you got atmosphere. Okay, so notice the decimal is right there. When you have a trailing 0 with a decimal value in the number, that becomes significant. So that's a significant. So there's your 3rd significant digit. Because you got a decimal point in the number. Trailing zeros count if you have a decimal number, which is why they do that in the ALEKS. The reason they would do 720 with a decimal is to tell you this is significant. Because if you take the decimal off, there's no decimal. You don't know whether that 0 is significant or not. So that's essentially the idea. So there's your unit conversion. It's pretty simple. Like I said, I don't think you have to do PSI for this one. You don't have to do bar. I just set it up so that you just have to do torr, atmosphere, and kilopascal. Those are kind of the 3 big ones these days. Like I said, the PSI it's an old imperial unit, still used here in the United States, but even now you're starting to see it disappear slowly. Okay, so let me come over here and move on to the next topic, which are the gas laws. So we're going to do section 10.2. So let me create a new one. And I'm just going to go ahead and write them down for you right now, what the 3 gas laws are, and then we'll do the ideal gas law tomorrow. So the first one is called Boyles Law. And the most common form of Boyles Law is P1V1 equals P2V2. And we're going to call P1 the initial pressure of the gas. We're going to call P2 the final volume. So notice I'm switching from IF, initial final, to 1, 2. It's just a little bit more common with the gas laws. Final pressure of a gas. V1 is the initial volume of the gas, I'll stay consistent. And then, of course, V2 is the final volume. And we're going to make an assumption here. There's an assumption in Boyle's law. We talk about assumptions a lot in the sciences. We have to make assumptions because the universe is very complex. It's very, very complex. So if we don't make assumptions, generally our laws or our rules will be incorrect. So the assumption here is that the temperature of the gas is constant. Okay, and so there's actually 2 assumptions. The second one is the amount of gas is constant. Okay, so the amount of gas is constant and the temperature. If either of those 2 are not true, then this Boyle's law, called Boyle's law, is invalid. It no longer is a valid law. So it's only valid under these conditions. Okay. P1 V1 equals P2 V2. Very simple relationship. And there's all kinds of ways we could talk about it, but I'm going to leave that behind for now. The second one is called Charles's law. Although sometimes this is called the law of Gay-Lussac, because Gay-Lussac also studied this issue. And this one says that V1 over T1 is equal to V2 over T2. Okay. And you can imagine, you know, I'm going to define these. V1, initial volume. We're talking about gases, so I'll just, you know, just to speed things up, I'll just say initial volume of the gas. I'll just say initial volume. V2, final volume of the gas. T1, initial temperature. T2, final temperature. And just as with Boyle's law, Charles's and Gay-Lussac's law have two assumptions. Pressure and the amount of gas constant. So I put a comma there to indicate that both of those have to be constant. You can't change the amount of gas and can't change the pressure. That would make this law invalid. Okay. Tomorrow we'll look at problems where you can combine everything together. It's called the ideal gas law. Third one is called Avogadro's number. Oh, sorry, Avogadro's law. Avogadro's law. And this can be written as V1 over N1 equals V2 over N2, where V1 and V2 refer to volume. All right. And then N1 and N2, comma N2, refer to moles of the gas. So this one says that the volume, the initial volume of the gas divided by the number of moles of the gas is equal to the final volume of the gas, right? I didn't write V2 for final volume because it's the same notation we were using for the previous laws, divided by N2. So the final volume divided by the number of moles of gas. So you can see here, this one has moles of gas. So the amount of gas is changing, okay? So again, we have assumptions here. P and T are constant. Okay? And what these three laws allow us to do is to predict how a gas will change if we change the conditions of the gas. It is useful to think of the idea of what we call a state. Now, in chemistry, when we use the term state, we often refer to whether something is a solid, liquid, or gas. But in terms of gases, we can talk about the state as being some combination of pressure, volume, and temperature. And that would be called the state. So for example, I might say the pressure is 1 atmosphere, the volume is 2 liters, and the temperature is 20 degrees Celsius. That would be a state. And then we change the state of the gas. So since we're changing it, we might want to call this P1, V1, T1, and then call this P2, V2, and T2, commas in between. Now you might ask, well, why didn't I put moles in there too? Isn't that part of the state? Well, it turns out if you know three of the conditions of the state, you can just calculate the fourth. So if I know the pressure, volume, and temperature, I can just calculate the number of moles. So we don't need to put it in there, even though that is part of the state. So this would be called the initial state. And this would be the final state. So you'll see a lot of problems like this, where a balloon at sea level at some temperature undergoes, some process where it goes up in the air and the pressure of the atmosphere changes as it goes up and the temperature changes, right? So that's a change of state for the gas. If we go back to our conditions we did when we were talking about work, cylinder, right? Of a gas in a cylinder or a mixture of gases in a cylinder. We're essentially observing a change of state in those processes, right? If the gas is expanding, that means the volume is changing. And very well, maybe the pressure is changing, or maybe the temperature is changing, or maybe both are changing. Maybe all three are changing, right? So that's a change of state. And that's a very important concept when we do energy calculations, which we did a little bit of that, right? We did energy calculation. Actually, we did it. When we did calculate the mechanical work that's done from the expansion of this gas, that's a change of state causing an exchange of energy. So when you change the state, you have an exchange of energy. It could be in the form of heat, it could be in the form of mechanical work, but the internal energy or the enthalpy of a gas will change if it undergoes either expansion or compression, right? And at least under certain conditions. So it's useful to think of that. These are essentially laws that are connecting the states. So we have an initial state here and a final state there. Notice it only has two variables, pressure and volume. It doesn't have three. I said you got to have three. Well, the reason that it only has two is because for this law to work, the assumption is that the temperature is constant. So if you make one of the variables constant, we can just remove it from the equation altogether. And so that's the usefulness of Boyle's law and Charles's law and Avogadro's law, is that they're taking these initial and final states, which have three variables. They really have four, right? But we said we could get the fourth from three. And it is under specific conditions, reducing them to even something more simple. Just two variables, pressure and volume, in the case of Boyle's law, volume temperature, in the case of Charles's law, and volume moles in the case of Avogadro's law, okay? Now, we could argue that there's really no need to know all three of these because there's something called the ideal gas law or the combined gas law that will take all of these and we can just manipulate that one equation and get all three of these, but that's fine. This is typically the way we teach it in general chemistry, is we teach you these first three and then we combine them to give you the combined gas law, okay? So we'll look at that. Probably not today, but maybe tomorrow. Okay. So then it's just a matter of doing these problems, picking the one, picking the right law. If the pressure is changing and they ask you what happens to the volume, you're going to use Boyle's law. If the volume is changing and they ask you what happens to the temperature, then you're going to use Charles's law. If the volume is changing and they ask you, something about the amount of the gas, because remember, moles is the amount of a substance, then you got Avogadro's law. The Avogadro's law, sometimes the questions are a little tricky, but we'll go through it. Okay. So let me show you an example. Okay. Understanding Boyle's law. Well, this one's telling you P1 V1 equals P2 V2 right there. Okay. A cylinder is filled with 10.0 liters of gas, right? Remember that volume is the units we often use are liters. You'll see that a lot. Milliliters are liters. So a cylinder is filled with 10.0 liters of gas, and a piston is put into it, right? Okay, so they give you a little diagram here. The initial pressure of the gas, P1, right, is measured at 145 decimal kilopascal, right? That's the unit of pressure. So we have P1. It's filled at that pressure. The volume is 10.0 liters. So see how those two numbers are connected? 10 liters when the pressure is 145 kPa. That's V1. The 10 liters is V1. So you got P1 and V1. The piston is now pulled up, expanding the gas, right? Until the gas has a final volume of 51 liters. Well, that's a pretty big change in volume right there. That's a huge difference, right? Calculate the final pressure of the gas, right? So if you take a look at these numbers, 10 liters, 145 kPa, those two go together. That's P1 V1 or V1 P1. And then now the pressure goes up, your volume, your final volume is 51.0 liters. So that's your V2. calculate P2, right? Calculate the final pressure. That's all they're asking you to do. Okay. So let's take a look at it. It's what, 145, 10, and 51. Okay. So let me show you this one. Boyles, I'll come back to that. Okay. So P1, 145 kPa. V1, 10.0 liters. P2, we don't know. V2, 51.0 liters, right? So now, did they, I'm actually going to go back and read this. I can't remember. They nowhere in there did they say the temperature was constant. So I would argue that that is a poorly written question. They did not write that question well. It does say use Boyle's law. So in a sense, they're saying assume the temperature. It's implicit that if you're using Boyle's law, the temperature and the number of moles of gas are constant. But I would like to see that explicitly written. Okay. But they say use Boyle's law. P1 V1 equals P2 V2. So the question was, what's the final volume? I'm sorry, the final pressure. So that's your final pressure. Other than that, it's pretty easy. So we want to find P2. So algebraically, we divide both sides by V2. And that gives us P2. So we need P1, 145 kPa. There's your P1. Your V1 is 10 liters. And then your V2 is 51.0 liters. And that's going to give you your P2. Now notice the units. Liters cancel and you got kilopascals. Okay. The result is 145 times 10 over 51.0, and you get 28.4. Look what happened. The pressure went up. I'm sorry, pressure went down. It decreased. So one aspect of Boyle's law, in terms of its interpretation, is that the pressure times the volume is constant. P times V is a constant, right? That's essentially what Boyle's law is saying, is that the pressure times the volume is constant. So if the pressure goes up, the volume has to go down, right? If you take something times something and that's equal to a constant, if one of them goes up, the other one's got to go down. If you double one of them, the other one's got to go down by half, right? Or go down by 2. That's just mathematical relations, right? So it ends up looking something like this. If you do pressure versus volume, you get something like this. It looks like that. So was that a hyperbola? So, as the pressure goes down, the volume goes up, right? So P1 V1 equals P2 V2 is just a specific way of writing P times V is constant. Okay, so sometimes you'll see Boyle's law written that way. And I won't go through that issue. All right, let's take a look at the second one. So the second one is, solving applications of Boyle's law. Okay, so this one's a little more involved, I guess. Solving applications of Boyle's law. So a gas storage cylinder in an ordinary chemical laboratory measures 4.9 centimeters wide and 20 centimeters high. This is the label on it. Contents, nitrogen gas. Pressure, 10.9 atmospheres. If the cylinder is open and the gas allowed to escape into a large empty plastic bag, what will the final volume of the nitrogen gas, including what's collected in the plastic bag and what's left over? Oh, I'm sorry. Let me read that again. If the cylinder is opened and the gas allowed to escape into a large empty plastic bag, what will be the final volume of the nitrogen gas, including what's collected in the plastic bag and what's left over in the cylinder. Okay, they're awkward wording just because sometimes simple things require awkward wording. Write your answer in liters and then round your answer to 2 significant digits. It's 2 because of those measurements of length and height, or height and width. They only have 2 significant digits. Okay, so let's take a look at it. Okay, we're starting with a cylinder. Okay, and this has the nitrogen gas in it. All right, let me put some of these numbers in here. So your pressure is 10.9 atmosphere. And it's 4.9 centimeters wide. So it's 4.9 centimeters here. And 20 centimeters high. Okay. So that's all of our initial information. Again, it doesn't say anything about constant temperature, but yeah, should say something about constant temperature. It doesn't. It's just an oversight by the people that wrote these questions. Okay. If the cylinder is open and the gas is allowed to escape into a plastic bag, a large empty plastic bag, what will the final volume of the nitrogen gas, including what's in the bag and what's left over in the cylinder? What's that final volume going to be? Okay. Good. Excellent. So what will be the final volume of the gas in the bag and cylinder together? So they're actually asking you, they're making it easy for you by saying we're going to put them together. And that's what's we're going to call that our final volume. Okay, that's really what they're asking. So what they're saying is, look, you open this door, this little, I don't know what you call that, opening, you open this, and it's going to fill up the bag. But what will happen is with gases will just, it won't just all go into the bag. It's going to, some of it's going to stay inside of the cylinder. So it's going to fill up the bag. We don't know how big the bag is, but they're making it easy. They're just saying, just what's this total volume? So what's the final volume of the gas together? Okay, so here's what you want to do. We're using Boyle's Law. So V1, P1, V2, P2, just start putting in numbers. Now, the problem with V1 is they didn't tell us V1. They gave us the height. They gave us the width of the cylinder. Okay, well, that's not a volume. Those are heights and widths. But you can calculate the volume of a cylinder from its formula. The volume of a cylinder is pi r squared h. I'll put it capital H. Okay, where r is the radius of the cylinder, so half the diameter, half the width, and then h is the height. So h, that's easy, 20 centimeters. And then the radius is 1/2 the width, 1/2 the diameter. So that's 1/2 of 4.9. So is that 2.45? Okay, so there's your radius. So this would be pi times 2.45 centimeters squared times 20 centimeters. Okay, so let's calculate that. So that's our initial volume. So pi is 3.14159 times 2.45 squared times 20, and you get 377.1 centimeters cubed, right? Cubic centimeters, because you got centimeters squared times centimeters, so that would be centimeters cubed. Now our initial pressure is given 10.9 atmospheres, so that's easy. We want to know what the final volume is, so that's we're going to try to figure out. And then P2, that's now. P2. Very good question. What is P2 here? Well, the issue here is they don't tell us P2, but we're going to implicitly say the following. A balloon is a cool device because a balloon has a flexible membrane holding the gas in it, right? So here's what happens when you blow into a balloon. When you blow into a balloon, you're pushing in air because the pressure inside your lungs, it's kind of cool. We can make the pressure greater as it blows out of either our nose or our mouth, greater than the pressure of the air around us, the atmospheric pressure. So when you inflate a balloon, the reason it's inflating is because the pressure of the air going in is greater than the pressure outside. And you blow, 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 reach a point. Once that balloon stops expanding, the pressure that you're applying is equal to the pressure. So the pressure of the gas on the inside, that's the pressure you're applying, is equal to the external pressure, the atmospheric pressure. So what will happen is this plastic bag will stop inflating when the pressure of the gas, the nitrogen gas, is equal to the atmospheric pressure. Well, what's atmospheric pressure? 1 atm, right? So 1 atm. Okay. So anytime you look at the expansion of a balloon, the balloon will stop inflating once the pressure is equal to 1 atm. And that makes it pretty simple. Okay. So it looks like we have almost everything. We just need V2. So P1 V1 equals P2 V2. We want to know V2. So we divide both sides by P2. And there we go. Now, I don't know what the units are going to work out to. We're going to have like centimeters cubed for volume. I don't know what units they want in this question. So let me come back here. And on mine, I have to actually look and see what units they want. They didn't say what, they just, oh, I'm sorry. They said in liters. Oh, they did actually. I didn't read that question very well. Okay, they said they want it in liters. Okay, so we have it in centimeters cubed. So there's an issue. We have to get that into liters. Okay, so let me do that before we put everything in. I'm just going to put the pressure in here. P1 is 10.9 atmosphere. V1, we need to have that in liters. So I haven't put it into liters. So we're going to do a conversion there. And then P2 is 1 atm. So let me do the sidebar here. Try to do that here. Okay, so we have 377.1 centimeters cubed. So how do we get that into liters? Well, if you recall, I'm going to show you the easiest way. If you recall, when we got to chapter 4 or chapter 3, I think I was talking about density. 1 centimeter cubed is equal to a milliliter. It's the same unit, just a different name. It's also cc, right? It's also 1 cc, cubic centimeter. So, oh, that's good, because when we did chapter 4, we said 1,000 milliliters is equal to a liter. So that means 1,000 centimeters cubed is equal to a liter. So that's cool. So 377.1 centimeters cubed, and 1 liter is 1,000 centimeters cubed. It's not as hard as I thought it was going to be. So you get 0.3771 liters. So that's easy. 0.3771. We only need 2 significant digits. So V2 would be 10.9 divided by 0.3771. And to 2 significant digits, this is 29 liters. And let's see if that makes sense. The initial volume was about 0.4 liters, right? 0.3771 is about 0.4. and our pressure was about 11 atmosphere. The two of them together is a constant. So if I multiply 11 by 0.4, I get 4.4. So P1V1 equals 4.4, right? So that means P2V2 has got to equal 4.4. And if our final pressure is 1, right? If this is a 1, that means that this has got to be, well, wait a minute, that's a 1, that's got to be a 4.4, right? So there's something wrong with my reasoning here. Let's see, P1V1. So 10.9 times 0.3771. Yeah, it's about 4.1. Oh, I just did this wrong. I'm sorry. It's not 29. So there you go. My check helped. Thank goodness. So 4.1 liters. Excellent. Okay. I don't know how I must have put something in here. But yeah, 10.9 times 0.3771 is 4.1. There we go. Okay, good. So I'm glad I did that check. If I had not done that check, you know, P1V1 should equal 4, somewhere around 4.4. I wouldn't have got that answer checked out right. So I did that and got the right answer. Okay. Excellent. Glad I did that. Okay, let's see. Do we have enough time? Okay, I don't think we really have enough time to do Charles or Avogadro's. So what I'm going to do is I'm going to end it right there. So tomorrow I'll talk about, a little bit slower than I thought I would. Tomorrow I'm going to talk about Charles's law and Avogadro's law. So I'm going to go through those. Charles's law is important because it's going to introduce us into the real logic of, or the importance of using a different temperature scale. So I don't want to go through that very quickly because we have to talk about Kelvin, the thermodynamic temperature scale. So we'll talk about Charles tomorrow. We'll talk about Avogadro's tomorrow. Avogadro's pretty quick. And then we should have time to get a little bit, at least, into the ideal gas law, which is section 10.3. So we've done 10.1. We're in the middle of 10.2 right now. We've done Boyle's law, but not Charles or Avogadro's. And then we'll get into the ideal gas law as well, probably tomorrow. Okay. So there we go.